right, so a couple of things to say hi. I'm not your, I guess, your usual presenter, but I am a designer. And it's funny that every time Matthias kept saying designer in the last session, I was like, well, who is he talking about? But I focus on the human. So I'm going to be talking about that part, which is the complement to the earlier bounded context conversation, because I think all of those things make up a system. And the way that we separate them in some ways is not necessarily optimal. So, quick thing, I learned this from Guy Kawasaki. So I'm only going to do a quick introduction of who I am, some definitions, because I'm going to be using these words all the way through. Then I'm going to introduce the membrane metaphor, and I think that that's going to be interesting, talking specifically about APIs, because APIs is system design. But we don't always approach it that way. And then some examples where I've used what I'm talking about in my work, and then I'm hoping we have time for questions. So, first definition, everybody should be familiar. APIs can be modeled using the metaphor of semi-permeable interaction boundaries. And where I came to this problem is you get these wonderful, high-fidelity, pixel-perfect designs, and me, the annoying person, saying, you have to build it exactly like that, without any awareness of the system and then all the things that you're going to have to do to make it technically feasible. The best that my colleagues will do is they'll put red lines all over this thing and tell you all the things you should not do, and then that's what you're going to have to go build. So this is going to be about that. I already said hi. A little bit about me. I'm actually I could call myself design principal or troublemaker where I live. And I had to pick a technology. I used to be a technical architect, building and designing data centers. So I mainly live in the front end of where technology is, but looking at the whole spectrum. And I describe myself as a computational designer. And what we do is that we take our mastery knowledge of people, systems, networks, and combine them. And that's why I think a lot of the stuff that you guys are talking about for DDD is just a facet of this. So we're trying to do the same thing, but I think we're using the wrong language. We're using our language to describe something that is even bigger. And so we need new language that we build collaboratively together in order to do that new thing. And so my day-to-day is unwinding a lot of balls of mud and figuring out how I can put people in them and then work with my technical colleagues to try and not make them balls of mud again. So computational design, which is where I focus, is about designing for billions of people. That is naturally variability. So again, when someone was saying, oh, these things change and that's wrong, no. We should design for systems built in, it's going to change, and that's just a fact of life. And doing that with billions of people in real time and at scale. So it's not just about beauty. There was another comment. And it always makes me smile when developers talk about ugly code. What is technical about ugly? It's an aesthetic, and it's an emotional word. Elegant code. What is technical about elegant? Again, it's aesthetic, it's emotional. So you're using these emotional words to talk about something that is technology, but you will never admit that it's emotional. So design isn't about beauty, it's about market relevance and meaningful results, yes, but beauty is an important part of it. So let's go through a definition. So API, mechanism for connecting two or more computers together. No, is connecting two or more systems together. And those systems could be software, technical, a ship, a person, okay? The other thing that really bugs me about API documentation today is that it never tells you how to actually connect these things together. You just get a whole list, usually in alphabetical order, and then you're supposed to figure out that you call the engine, new engine, before you build the better car. It's like, how am I supposed to know that? But that's where a lot of our work is, microservices, all of that stuff. We need to build in that understanding, just like Matthias was talking about, into APIs, and I pick APIs as an example. Semi-permeable membranes. This is about physics. It's a certain grounded biological way and behavior where a biological layer, or it can be synthetic, allows only certain molecules, objects, to pass through it, and in a particular direction. Osmosis is the physics that describes that process. So we need to start having descriptive language that talks about those interactions beyond bounded context and all. What is going on between that context and that context? Is it that everything moves in one direction and then piles up over here, and then there's a limit to what it can take, and then what's the balance? We need to have words for those things. So I stole liberally from biology because they have words for that. And so the physics of osmosis is that molecules of a liquid, not any other object, just liquids, pass through a semi-permeable membrane. The membrane is API, okay? Here's the contract. If you're a liquid and you're a molecule of a liquid, off you go. Anybody else, hold it. So if you have a less concentrated solution, then they will still work to balance the water molecules, but then some other weird stuff starts to happen. So here's an example. And this always breaks my brain every time I see it because it seems to be counterintuitive. You have a beaker, like my glass. I don't have physical semi-permeable membrane. I'm still trying to find if I can do this in an actual experiment. You put it in the middle of this glass, and you already have water in it, and then you put salt on one side, and then the water goes up, and you're like, what the? There. And that's because the physics, the contract says, if you are a molecule of water, to balance the osmotic pressure, because that's the thing that's driving it on both sides, so it's equal, because that's your aim, then this is what's going to happen. So, and I'm very focused on the interaction level, because as a human being, most people don't know, and we don't expose what's going on in a software system. So they only see what the software system is doing. And what it's doing is, I put salt here, and then this thing happened. Okay, that's how it works. It may or may not be right. It might be an anti-pattern, whatever, but we take that as a heuristic, and then we keep using it. But is that the way that you designed it as a software designer? Maybe, maybe not. So one thing that people are really good at, and I think developers forget, is the concept of cognitive dissonance. People can hold 2, 3, 50 gazillion different competing ideas in their brain at the same time. Every software developer, myself included, what do we talk about? It must only be this. It has to be prescriptive. It can only be one. It has to be more. Nobody's talking about the fact that there should be that tension built into your system. And that tension is also part of where change comes from. So some perspectives might seem like they contradict each other, but actually it's a balance because you're always trading off, right? And you have to remember that your system, back to my first definition, billions of people, different people have different aims at different times. We have time zones. Nobody's all up at 1 a.m. in the morning or in the afternoon because everybody's 1 a.m. is at a different time. So we need to cater and think about, and because that's the physics of the world that we live in, that's what we should be building for, not some artificial, okay, this is how it's going to work. Does it work for people? No. Does it work for cognitive dissonance? No. Does it work for the physics of the world that we live in? No. Then how is it going to, it's not going to work. Oh, so one example that I give is that something can be hot and cold at the same time. Now, that depends on what your objective is. Me, I can have cold feet and a hot head, warm hands, cold body. I'm still one object, but different parts, composite parts of me, then have their own properties. So this is something that is a pet peeve of mine, and that's why it's here, not that it's related to talk. An assumption is a statement or a thing, and this drives me crazy, that is accepted as true and certain without proof. We just talked about the scientific method this morning. And the thing that comes out of architects' mouths is, I made an assumption about that. What is scientific about making an assumption that is not qualified? So I have a proposal. I'm not just picking beef with everybody. I'm on a mission, and I recommend using presumptions instead. Because what presumptions are is you are accepting something as true with a probability. And that probability can be 0 or 100. And so what you're doing, just like Dave talked about this morning with the experimentation, you're saying, okay, I'm making a hypothesis where this probability, I think, is 100%. And then you try and drive your experiment, and then the open real-world system kicks your ass and says, no, it's 0. And then you go back and you try again. So last thing, a model is a thing used as an example to follow or imitate, and we talk about models all the time. But George E.P. Box, in 1976, put this in 3 scientific papers and said, essentially, all models are wrong, but some are useful. And this is another phenomenon that I see, where we get so attached emotionally to our models that you will pry that thing from my cold, dead hands before I will give it up. So if you start from this position that it's useful to help me to get to a certain point, but at some point I'm going to have to let it go and replace it with something else, then I think that that is a better starting position to be in. And I really like this quote because I will unpack it, but it says, there's no story that is not true. If I translate that, the way I translate is that everything is possible. But we have physics. So whilst everything is possible in your imagination, in the real world, given certain constraints, only certain things are possible. But it doesn't mean that it's not true. And then a couple of humorous examples of a model is in 1963, the partial fossilized skeleton of a woolly rhinoceros was discovered in Germany. This is now the Meiderberg unicorn. Somebody put this thing together and said, that is the story I'm telling. It's true, but okay, it's not true, but it's actually one of the worst fossil reconstructions, model or story in human history. And we've been doing this thing for a very long time, so it's not new to software. So I think we need to be a lot more self-aware as people about how we operate and how we function, and therefore the impact that we have on the thing that we're making. Another one, 1781, a Swedish taxidermist was commissioned to commissioned to stuff the remains of a lion. He had never seen one. The king comes up to you and says, okay, you're a taxidermist, right? You're a software developer. Okay, make me this lion. Or if I don't do it, my head goes. If I do it, then I get money and food for my family. All right? And so the guy did the best he could, did some research, looked at the heraldry flags and whatever, and that was his best effort. This is a male lion. There's no mane. And it's still on display in Grisham Castle. And again, it's anatomically correct. Is it possible? Is this a story that is true? It's happened, but it's not correct. So with all of those things that I've said, I'm happy to be challenged on my model of looking at APIs as membranes, because it's just a way for me to try and think through and apply this set of physics to a problem that I'm having in software and design it, because there are people involved in the real world, okay? So the things that you tend to dismiss, the other thing I do is I love quotes, because they're little snippets of wisdom for me, so tough if you don't like them. I'm going to have them all the way through my presentation. The thing that you tend to dismiss as mistakes, perhaps you should take seriously. They weren't what you intended, but that doesn't make them wrong. It's a possibility. And it's Brian Eno. You guys might know of his oblique cards. And I love the guy, the way he thinks. He's a musician, and he's basically writing software without writing software. And the thing I would add, or complexity, or maybe it's complicated. Okay? I'll talk about that in a little bit. So I try to think of my problems and challenges, especially as I'm including the human aspect in 3D space. It gives me more room to move. If I could think in 4D space, I would go for it, but I think this is the limit of my projection. And so this is one of the things that I'm proposing. And I'm using the simplest shape, which is a cube, 6-sided. And so if you take that 3D space and then you flatten it, because when I was looking at Matthias's diagram, if he had taken the, input, in, put away, and then out, that's one plane. And then the thing he was talking about with efficiency is another plane, then you would have been able to look at this thing in 3D space. So that's the sort of thing I'm trying to do. And so we're flattening it. And so the first plane, I have named these things because then it helps me to remember to apply them. And the first one is complicated, consisting of many interconnected parts. What we build in software is hella complicated. It's millions of lines of code. It's tens of thousands of objects. And some of people in this room walk around with that entire system in their head. And then every so often they remember to document it for the rest of us ordinary people. But so that's complicated. And then the next one is a plane. Because if you start laying things out on a plane and layers, and this might also be influenced by the fact that I'm a designer, and if you've ever heard a designer in-joke is, have you named your layers, right? So you have layer 1, layer 2, layer 10,000. But in mathematics, it's flat, two-dimensional, and it can extend to infinity. Boundary membrane is the limits. So again, you already got your contradiction. If this thing is expanding to infinity, how can it have boundaries? We impose boundaries on it. And then dimensions, you've got different sides. Complexity. Now, the complicated is about the things that you know. That's known knowns and even known unknowns. That's your assumptions or presumptions. Complexity is the things I have no freaking idea. So you would probably start with hypotheses and experiments just to try and figure out what is going on before you then figure out all the different pieces and reduce it to figure out what to do. And the place where I live is the interface domain. I feel like I'm switching between here's the human, this is what they need, and then here's the system, and this is what it does, and can you two meet in the middle and play nicely? And so now what I'm going to do is I'm going to go through some personal, concrete examples of where I've applied these definitions and principles that I've talked about. And if you have questions, then interrupt and stop me, and we'll keep going for the time, because there'll be quite a few. So, another favorite quote. It is better to do the right thing, wrong, and improve. Don't forget the and, improve, than to do the wrong thing right. So if you're not asking why about something, and you're not asking what it is, and you're only asking how do I, then you're at the back half of that quotation. And this is by Dr. Russell Ackoff, who is a systems thinker, operational theorist, and a whole bunch of other things. And he lived and worked at around the same time that Peter Drucker, the other management, his name escapes me, the other management consultant was around, and they were trying to figure out some of these issues and challenges. Okay, so in order to address complexity, if you're not working with someone else who is not just not you, does not work in your field. So if you're a developer who has never worked with a designer, a data scientist, a business analyst, anyone else, any other function in your company, then what you're building is what you know. Not what you don't know when you're trying to solve. That is not problem solving. Complicated is not problem solving, that's recipe building. And what you need to do is apply both the analysis process and the synthesis process. The analysis process is you take the problem, not solution, problem apart. You figure out how each of those parts function, and then you assemble and aggregate the parts in order to explain the subsystems. Synthesis is the opposite. You step back, zoom out, and you look at the thing that contains your problem. And then you figure out how your problem relates to that wider system and what its function is or should be, and then also explain its role from that perspective. So if you think about it as two triangles, you zoom out to do the synthesis, you have a problem already that's been stated. Usually that problem is the wrong thing. So you need to figure out what the right thing is, and then, yes, do it badly, but this is about choosing the right thing. So it becomes the proposed problem. And then the annoying thing that I do with every one of my colleagues is, I'm sure if you've worked with designers, the first thing they're going to say is that the problem? Let's step back and look at that. So you go and find 50 other gazillion problems and say, okay, let's kind of just work through, and you're starting to do this with domain-driven design and event storming and a whole bunch of other things. So you eliminate, and then once you've identified, you've validated your assumptions, then that is the problem. And the other cool thing about this approach is that it's 10 times faster than building something, figuring out that it's wrong, and then choosing some next random thing and building it. If you have 5 variables, that's 125 combinations. If your answer is 125, you're going to waste time if you start from 1, working your way through, eliminating all of those in order to get to 125. Whereas if you do this, you'll get there 10 times faster. Planes, dimensions, and interfaces. The other thing that you will notice is that other than complexity, because that is just such a big problem for us that we don't know what we don't know, I sort of handle that separately. Everything else I kind of combine, mix and match. So one of the things that I've observed and I've noticed is that regardless of the context of the problem, we always flatten it into a 2D space. Okay, that's fine. But then we also prescribe what that 2D space should look like. So I'm using my 6 planes, and typically we would arrange it like that, capital T. It could also be this kind of funky Z. Or it could be a small t. Or if you then slice across it, that's the same thing, folded back on itself. So there are different ways of looking at your problem and then defining what it is. And then if you're making a solution for this, it's not the same thing as making a solution for this. Even though they're the same areas, they're equivalent, but they're not exactly the same. Okay, so why do I bring that up? This is one half of my life. I spend time drawing these things to some fidelity. Low, because we're experimenting and figuring, is this what you meant? No. Then I go capture again. Is this what you meant? No. Yeah, it's that one. Then I have to flatten, literally, and draw like 200 screens in order to be able to account for every single interaction, every single thing that's going on. And then, I mean, to this degree, this drives me nuts, but this is what I have to do. And then you start to draw. This is my big ball of mud, because now all these lines are interactions between these screens. Some of them are APIs. Some of them are talking to microservices if it's designed well. Otherwise, it's running all the way down the stack from the API, so directly to the database or whatever, because somebody pressed the button. I see a few people shaking their heads. Yes, because, again, we haven't done the planes and the layers. So, yeah, you get this spaghetti. And then the other thing that, where I came to this problem is, how do I identify which one of these things should be an API, and in which particular order, and what's the contract from something like that? So interfaces, boundary. I didn't know about bounded context, okay? So I came to this. I've been working on this model for like 10 years. So when I started hearing in DDD, and I kept hearing this thing called bounded context, it's like, what? And it's kind of the same thing, but coming from a different area. And complicated, because there are recipes and there are things that we know how to do. But the problem is that we start with those first, rather than identifying what's complicated. I know it, but it's just a lot of work. And what don't I know anything about at all? So I need to be experimenting there and figuring that out, right? So why completely create something when somebody's already done a lot of the hard work? So one of these, you've probably heard about design systems. Designers use them a lot. And I prefer, and I really like Brad Frost's version. It's based and inspired by chemistry. Maybe I'm partial. My first degree is in chemistry. And what I did was I modified and added a couple of pieces right at the front. So particles, to keep with the chemistry theme, or elements. And these specify things like colors, fonts, styling, backgrounds, borders, because those are predefined, for example, from a brand. They're also the things that everybody wants to change. And then when they change them, they want it reflected all the way through and just bubble through all of the interface, because that's what the human is going to see. But guess who has to implement all of that? The developers. So you've got particles, because they're subatomic entities, atoms. These are particular constructs. They're like Lego blocks. And so you have the really thin 8-bit Lego block, you have the 6 rectangular Lego block, you have the square, and these are predefined. So once we've figured out what problem we want to solve, then we look at the Lego pieces and see if we can do a few versions of the model, validate the model, and then we want to build the real thing. Now, some of those Lego blocks that we need might be missing, so we have to create new ones. And again, this is where the APIs come in. When you combine those atoms, you get molecules. When you combine molecules, so a molecule is like the molecule of water. I've never seen a molecule of water. I don't know if anybody else has. I've seen a body of water, which is multiple. So that's usually the compound or the organism. And that's usually what we experience. But what developers make are typically atoms and molecules that no one's ever seen. So how do you know that that's going to build into a valid compound and it's stable, and that will build into an even bigger structure, which will then be stable? And then the other thing, which is to do with placement, you have templates where you've prearranged certain things and patterns that you know that work for pages. And then the pages are the instances that you produce. So this is where I live. I started with, I think, 3 layers of this. This is the model that I use for most front-end systems that I build. And after being here this week, I would actually rename the controller as the orchestrator, because that's what it's doing. It's not controlling, it's actually orchestrating. Okay, you stop, traffic warden, whatever. And then I'm going to go through what this is. So when I talk about the osmotic membranes, I have rules and code or whatever it is in the system so that this is the traffic that happens in the application. It's built this way. So the content model only ever goes to the controller. You will never find any other thing in my applications that takes in content, because what's missing here is that the view model is effectively the store. And then what you do is that you have stores at different levels so that you can do caching and stuff and things like that. So when a developer says to me, this is taking too long, I said, you cannot compromise this as far as an experience for the user. So then we start trading off, can you cache this? And then, this is really expensive. Can we only do it once an hour? That sort of thing. And so when I talk about osmosis, that means that if anything else, or if anybody else, and people have done this, tries to write in the pattern, get data from the controller or the orchestrator, you'd be like, no. What are you? You're a pattern? No, it's not going to happen. So you put the physics of your osmosis, I don't know of another word to call it, and build it in. Okay? So I'll take you through a scenario. So typically when you get data from an API, it looks like this. JSON. I've been looking at epoch dates, I don't know, for 2 decades, and I still can never interpret them. And so what we're going to do is we're going to go through and show how you would apply osmosis to translating that. So the first thing you do is you translate that long number to January 23rd, 2018. And you think that your job is done. No. Because in the person's browser is the font that they prefer, the font color that they prefer, the settings that they prefer, and a whole bunch of other things that they prefer. So at this point, you need to be able to take that information to style that text. You usually have a default, if people don't say anything, that you would present that with, but if people have preferences, the feedback from the user and from the system starts from here. So you have the date, human readable, and then you take all of their preferences, otherwise you apply the defaults, in order to make it presentable. And then you've got the things like the subatomic particles, which says because this is on my branded site, then the background is going to be this color, the boundary is going to be this color, and the text is going to be 000 hex, unless they're using assistive technology, in which case they completely change all of that. And then you've got a bunch of building blocks. So you've got the text boxes and check boxes and text areas and text strings and a whole bunch of things that rather than going through this repeated every single time, you've got those locked in and then you just literally stamp them like your Lego blocks. Then at the composite layer, you start assembling your Lego blocks. So again, if you're calling the API, and you want to do composition, and then you want to go to the controller to get a piece of data. No, that is not happening. You would have to literally rewrite that application in order for you to be able to do that, because that's the physics that we've built into the application. Then the composite layer allows you to then do things like this on the fly. So if you want to change the way that donut is visualized so that it's a bar chart, you can do that. Because all you're doing is you're taking the layout, the data's the same, the colors are the same, everything's the same. You're just taking the layout and doing an alternative at the composition level, replacing it with a different view, and any additional information that it would need to make it happen. And then the last thing is how you combine them together. This is the difference between Dave's box of Legos and his kit. So a lot of the stuff that we do in user interfaces at this level are kits, because we are people. We've got two eyes. We only have so much attention. There's certain behavior that we do every time. So start with the kits, and then if you find that there's some other variation, go back all the way to the complexity layer, do the experimentation, validate it, and then build it up. So you've got that whole set of behavior built into the system, but then we're reusing what we know and what works. So then you got the page layer, and then you end up with pages that look like this. But you've got 6 layers underneath it where you can mix and match and move stuff around. All of that is built in for this kind of application. So reminder, right? These are the contracts, the osmosis physics that I've imposed in that particular application. For a different application, if it was more data intensive, for example, for Internet of Things, I would have a different set of physics. Then it's easy to document, it's easy to update, it's easy to maintain, it's easy to pass it on to someone else. It's understandable. The model is clear, and the model is in the code. So if you take that and apply it even to your microservices, how can you leverage it for that? I think it could work. I haven't personally done it. I'm talking to my engineers right now to see if we can figure out a way to make osmosis a bigger part of the system, but this is where I have applied this. So last thing, complicated, is for me, is this definition. These are all the pieces. So what I just described was the second row. But there's a row above where you start to compose and mix and match and put applications together. And then there's the domain-specific app. So I think this is where there's the overlap with domain-driven design, and I'm having conversations with a lot of my friends here trying to figure out, is that the same thing or different, or a window to that, or what? But you can see that it's related to the business, again, because this is what the business care about, this is what they talk about. And then decomposing this, yes, this is complicated, there are many moving parts and everything, but all of these things are known, or I have presumptions about the things that I don't know. But we've done this enough that you know, the impact of that will probably be not a lot. So machine learning, analytics, building a semantic model for the domain or the problem that you're working on, and then all the feedback and sensing from the outside. We've got an IoT connection service for that. There's a gateway, then it's down to the edge, and wherever those things live. This is complicated, but it's all known and managed and can be maintained, and people understand it. And that's why it's called, and the other thing I forgot to say on the complicated side is complicated is past tense, complex is present. And that's usually why we don't know, because we just haven't done it yet. So metaphor for osmotic, semi-permeable membranes and APIs is the 3D cube, right? 6 sides, going through and filtering your application through to try that, going all the way from unknown unknowns to the things that you do know and execute, and putting in the physics in your solution to make sure that only the molecules, objects that you have designed for are going to pass through those membranes. Flattened out, that's what it looks like. And I don't have a cube to give everybody, but the next time you say cube of sugar or whatever that is square, think about that. And that's me. Questions? Don't be shy. Yes?
I have to say I'm struggling with the osmotic part of your semi-permeable membrane. And osmosis, you characterize it as moving from an area of low concentration to high concentration. Can you elaborate on that in the API space?
So let me go back. So maybe I'm misusing, I wanted to keep it, but osmosis is about equalizing water particle pressure between a boundary. So what I'm doing here is I'm equalizing with the controller the presence and pressure, if you like, of the certain composite pieces that make up this system in order to deliver a page to the user. And the user is part of the system because part of what I'm reading is the preferences from their browser. No browser, nothing is going to happen here. So I would love a suggestion for what that thing should be called. But the pressure balance is mostly done by the controller based on who is talking to it and requesting. And then the other thing that is doing the pressure balance, for example, the view model actually takes or makes requests from the controller to read the inputs from the browser to supply it whatever it needs. So again, the controller is only ever going to pass what's requested, and if you try to, by the side door, which people do all the time, try to pass it, then it's just going to be ignored because that's not what the view model was expecting. So it's about coordinating. That's why I said I would change the name actually to an orchestrator or even a conductor. It is the manager of that request pressure and making sure that it's as defined. Does that make sense? Okay. Hopefully that answered your question. Anyone else? Yeah.
So once we talked about complicated and complex,
Yeah.
and something else that is more like understood or something. So what is the relationship between them and, I mean, there's some gap in between that. Can you elaborate on that?
Okay, so you're talking about where?
Before, there's the complicated, and then there's the complex.
Uh-huh.
Something like that. Yeah, and then there's the
This one?
exactly. Yeah. So what happens in between? Because you can't jump between one.
Complexity is all about, or complex is about the things that you don't know. And you would normally, you've identified something that you don't know, you have a hypothesis, and then you run experiments. Once you get a lock on that thing and you say, okay, I have a good idea, I have a valid model, not the lion and not the unicorn, okay? You're going to make a lot of those, but whatever you feel is appropriate, and you have the evidence for it, and you've also validated your presumptions and your probability is more on the 100% rather than the 0, then it becomes complicated because you don't have to invent everything, right? Like I did with Brad's model, I added the pieces that I needed, but everything else was appropriate and relevant, done. So the jump from complex to complicated is, complicated is you know what to do, there's just a lot of stuff. Complexity, I have no freaking idea. That's how I think about that. Anyone else? You guys are really quiet. Going, going. All right. Ah, okay. Yeah. Well, okay, let me back up here. Doing what? Okay, I'll give you an example that I use all the time. If I'm in my house on a Sunday afternoon or it's the weekend and I want to listen to music, the most I want to do is stretch my hand out and press a button. I don't want to make 50 gazillion different choices. If I'm a sound engineer recording an album that is going to be sold and I want to balance it perfectly, then yes, I want that desk. I don't want the button that just says play. So when I answered your question and I said yes, again, it depends on the purpose and what the person is trying to do. And so the sound engineer wants to have full control and be able to people are part of the system, wants to be fully part of the system and decide everything. My Sunday afternoon, the only thing I want to decide is I want to hear sound, right? And that's all I need. So yes, for context and where it's meaningful and where it's appropriate. And that's why I spend a lot of my time thinking and talking about how to have that variability built into the system, because then you can tune up and down however you want as the user. So, yeah. Anyone else? Alrighty. So I know it's, oh, yep. Okay, so the question, just I'll repeat it and so that I heard it right, is how do I use this model to identify and understand? Oh, the runtime. This idea isn't specifically about runtime, but as a result of looking at when I'm going through the complex or the complexity, it's like, okay, what is it that I don't know? So you were talking about errors and things that you don't think should happen. Well, why didn't you know that those things were possible? That's the first question I would ask. And then the second thing that I do is, I'm just going to run through this really, really quickly. Yeah, second thing that I do here is I have tracing at every level. So I know what is happening in this system. So the existing systems that I didn't build or I didn't use this approach, then the first thing I would do is I would go and add tracing. I've got 1 minute. Okay, I would go and add tracing for the system to tell me what it's doing rather than me assuming, right, and guessing. And then based on that information, I'm either going to take, okay, I have no idea, how do I fix this, experimentation, or, okay, there's an existing pattern to solve this kind of problem, do some research and figure that out, and then apply it. So I didn't mention it, and thank you for that question, but built into this is tracing. Because then I can validate that what I have imposed in terms of the physics is actually happening, right? So yeah. And I just got the 1 minute card flashed at me. So this is your last chance. Not everybody put your hands up. If you don't have any more questions, thank you so much. You guys have been a great audience. And